Hello, I'm John Edmondson. I'm here to talk about the 21164 microprocessor. The 21164 is an entirely new Alpha microprocessor designed at Digital in Hudson, Massachusetts. We're currently running 3 different operating systems on the Pass 1 silicon and have been running for several months. And the chip will be announced as a product within the next couple of months. Here are the key attributes of the chip. It's a 4-way superscalar design with in-order issue and out-of-order completion. It has a large on-chip second-level write-back cache. The pipeline is 7 stages long for floating point instructions and 9 stages long for integer instructions. And the design is characterized by an emphasis on low operational latency with a very fast CPU clock rate. The superscalar execution core is supported by a high-throughput memory subsystem. Here's a block diagram of the chip. On the block diagram on the left side is the instruction unit. Then there are 4 execution pipelines, the memory unit, the second-level write-back cache, a bus interface unit, and an optional off-chip third-level write-back cache. The instruction unit fetches and decodes instructions, handles register allocation and function unit allocation, and handles exceptions. It contains a 48-entry ITB, and each entry in the ITB can map pages ranging in size from 8K bytes to 4 megabytes. The instruction unit also has an 8K instruction cache that's a virtual cache. The execution pipelines are divided into 2 integer pipelines and 2 floating point pipelines. The 2 integer pipelines each can execute the virtual address calculation part of a load and store instruction. Loads can dual issue in these pipelines, though stores can't. The floating point pipelines are divided into an add pipeline and a multiply pipeline. The memory unit contains the first-level data cache, which is dual-ported, load and store merge logic, which I'll discuss later, a 64-entry DTB. Again, each entry in the DTB can map pages ranging from 8K bytes in size to 4 megabytes. The memory unit handles access ordering as required by the architecture and read-write conflicts as they arise. The bus interface unit manages the second-level write-back cache, which is a 96K byte cache, 3-way set associative, and is kept coherent in a multiprocessor system. It also manages the third-level optional off-chip cache, which is a direct map cache, and is write-back and kept coherent as well. The bus interface unit is also, of course, the interface to memory and I/O for the chip. Note that data moves on 128-bit buses at the pins and internally for cache fills of all sorts. Here's how the chip looks in silicon. The recognizable structure in the center at the top is the instruction cache. The large structure on the bottom, more to the right, is the data cache. It's larger because it's dual-ported. The 2 large structures on the left and right are the halves of the S cache, the second-level cache. Around the instruction cache is the instruction unit, and below that is the integer register file and the integer pipelines. Below that is the memory pipeline and memory unit. On the left side of the core is the floating point unit. The register file is in the center, and the 2 pipelines are above and below. On the bottom of the chip, around the data cache, is the bus interface unit and the second-level tag store for the second-level cache. There are 9.3 million transistors, and the chip is 16.5 millimeters by 18.1 millimeters. Okay, I'm going to talk about the instruction unit in more detail now. This is a diagram of the instruction issue pipeline. It shows the 4 stages, which are instruction cache, instruction buffer, instruction slot, and instruction issue. The instruction cache stage contains an 8K byte virtual instruction cache that's direct mapped, and a prefetch buffer that holds 4 blocks. Each block is 32 bytes in size. The prefetch buffer is also a stream buffer in that misses from the instruction cache can hit in the buffer, and there's an address cam for each block. The instruction buffer stage holds 128-bit instruction packets. That's 4 instructions in each packet. It can hold up to 2 of these. Only full, naturally aligned 128-bit packets are moved in and out of the instruction buffer. That is, there's no shifting of instruction data in this stage. The instruction buffer stage also offers time for decode. The next stage in the pipeline is the instruction slot stage. Now, instruction slotting is the process of resolving static execution conflicts. So, for example, if the staging register at the beginning of stage 2 contained 4 floating point multiply instructions, and as you can see, there's only one floating point multiply pipeline, those instructions can't all issue at once. That's a static execution conflict, and the stage 2 resolves these. For cache hit, data comes from the instruction cache into the buffer and is forwarded to stage 2 to the slotting stage immediately. In cache miss cases, data comes from the prefetch buffer into the instruction buffer and fills the instruction cache at the same time, so that filling the instruction cache is a byproduct of injecting instructions into the pipeline. Now back to the slotting stage. In each cycle, a 4-instruction packet can be advanced to the instruction slotting stage, and it begins working on this packet until all 4 of those instructions have been forwarded to the issue stage. If that doesn't happen in one cycle, no new instructions are fed in from stage 1. In other words, there's no shifting of new instructions into stage 2. The instruction slotter continues working on the instruction packet that it was handled originally until it's completed that packet. This can take 1 to 4 cycles or even longer depending on stalls. What the instruction slotter does is prepare a packet that could issue in parallel if there were no stalls at stage 3. So packets of instructions advanced to stage 3 are handled as instruction issue problem. And 4 instructions are advanced to stage 3, or up to 4 instructions are advanced to stage 3. And stage 3 resolves dynamic conflicts. Now, dynamic conflicts are register allocation problems, are register ready problems, and function unit ready. The only function units that can be busy, though, are the integer multiplier and the floating point divider. If all of the instructions in stage 3 don't issue in one cycle, no new instructions can be shifted in from the slotting stage so that it stalls the pipeline. Also, instructions are issued in order, so they're advanced from the slotting stage to the issue stage in order, and at the issue stage, if any instruction stalls, all the logically preceding instructions will be stalled as well. Now this quad issue pipeline is extremely simple, and it's designed for a very fast cycle time. The rigid rules that I've described in the slotting stage and the issue stage can sometimes lead to code placement effects on instruction issue. And sometimes compilers will pad instructions with no-ops to minimize these effects. This is usually a small performance effect, the last couple of % of performance. The 21164 recognizes 3 kinds of no-ops: an integer no-op that can issue in either integer pipeline and takes 1 integer issue slot, a floating point no-op that can issue in either floating point pipeline and takes 1 floating point issue slot, and a third form of no-op that's recognized in the slotting stage and takes no issue slot and effectively disappears in the slotting stage. Okay, so to keep this pipeline fed in the event of a cache miss requires aggressive instruction prefetching. So as soon as an instruction cache miss occurs, and that probes the prefetch buffer and it misses there as well, the instruction unit requests 3 32-byte blocks from the next level of cache or from memory, and continues to stay 3 blocks ahead of the stage 1 PC until either an instruction cache hit occurs or a branch occurs. Either of those events means that it's time to check again to see if the data is in the cache. The prefetcher is capable of supplying instructions at a peak rate that matches the instruction issue rate for integer programs of 2 instructions per cycle. That is, the peak issue rate for integer programs is 2 instructions per cycle, and this prefetcher can supply instructions at that rate. The peak issue rate for floating point programs is 4 instructions per cycle, and the instruction prefetcher can supply instructions out of the level 2 cache at 60% of that rate. In both cases, that's depending on level 2 cache hit. Okay, now on to the execution pipelines. This diagram shows the execution pipelines and the stages in the chip pipeline they occupy, including the stages in which the register files are read. The integer multiplier and floating point divider aren't fully pipelined, so they're shown off to the side of the pipelines. The integer pipelines can each do arithmetics, logicals, and loads. One of them can do multiplies and stores and shifts, while the other can do branches and jumps. The floating point pipelines can each do well, the floating point pipelines are divided into add and multiply. The add pipeline implements all floating point instructions except multiply. Note this, the length of the pipelines is determined by different factors. The length of the integer pipeline is determined by the stage at which memory exceptions are resolved. This is because exceptions are precise. Memory exceptions are precise in the alpha architecture. For the floating point pipeline, the length is determined simply by the number of stages it takes to execute the instruction. And it is because arithmetic exceptions in the alpha architecture are imprecise that the two pipelines can be different lengths. Okay, the next slide shows the latencies of operations in these pipelines. Most integer operations take 1 cycle. The exceptions are conditional move, which takes 2 cycles, and integer multiply, which takes between 8 and 16 cycles. Floating point operations take 4 cycles, and loads that hit in the level 1 cache take 2 cycles. We also implement a special case bypass for a conditional move instruction or conditional branch instruction dependent on a compare or logical instruction. In the example shown here, the compare is producing a result in R3, and the branch is branching on that result. These two instructions can dual issue, and that gives an effective latency of 0 cycles for the compare. Now I'll move on to the memory subsystem. Well, one key to performance is sustained throughput, and this chip is designed to be non-blocking. That is, the pipelines don't stall on cache miss. In the case of a cache miss, stall only occurs when an instruction is ready to issue and the data it requires isn't yet ready. To support this, and to support dual issue of loads in the primary cache is dual ported. And it's a true dual port. There's no limitation on the 2 addresses that can probe simultaneously. In the event of a cache miss in the primary cache, a structure called the misaddress file captures the misaddresses and optimizes loads by merging loads that are to the same 32-byte block. This is very similar to how a write buffer typically merges stores that are to the same memory block. The misaddress file is also the buffer that holds misaddresses while they wait to probe the second level cache, and if they miss there, to go into the bus address file. Note that this merging in the misaddress file can allow 1 fill from the second level cache or beyond to service up to 4 register fills at the rate of up to 2 register fills per cycle, all from 1 fill, 1 32-byte fill. The bus address file holds misses from the second level cache while they probe main memory or the third level cache off chip. It can hold up to 2 misses. Leveraging off the merging idea in the misaddress file, the bus address file can merge 2 32-byte reads into 1 64-byte read, because 64 bytes is often the block size for that level of cache in the memory system. This allows us to get onto the next true 64-byte miss and sustain 2 misses off chip at a time. A comment on the cache hierarchy. The dual level hierarchy on chip allows us to implement very fast, low latency primary caches, both in the instruction unit and the data unit, and it allows us to afford a true dual port in the data cache in the data unit, and the area cost that entails, and then to back that up with a large, high bandwidth second level cache, which very effectively supports these caches, and because it's associative and because it's mixed instruction and data, improves performance. Note that the first level cache is right through and the second and third level caches are right back, as I've said before. Now let's look at how the load merging algorithm works in detail. This diagram of the misaddress file helps explain the load merging algorithm. Now up to 21 loads can merge. You get that by multiplying 6 entries by 4 loads per entry, and that would give you 24, and then there's another limit that holds it down to 21 loads dynamically. Each time a load misses, it probes the misaddress file to see if it matches any of the addresses there. If it does, it might merge into that entry. If it doesn't merge for some reason, it will allocate a new entry in the misaddress file. Each of the registers in the misaddress file, in a given misaddress file entry, corresponds to data in one part of the fill on one part of the fill bus. The fill bus is 128 bits, which is 2 64-bit words. So each register number corresponds either to the low order or the high order word of a fill. And since a fill is 32 bytes, that's 2 cycles, each entry corresponds to a fill during the first half of a fill or the second half, that is the first cycle of a fill or the second half of a fill. So each register corresponds to a different 64-bit word in memory. So two loads that are to the same 64-bit word can't merge because they would require the same data at the same time, and that can't be done. So the misaddress file limits merging in that respect. Another limit on merging is that there's only one format field per misaddress file entry. This means that integer loads can't merge with floating point loads, as an example. The last limit is that merging, once a fill has started to come, merging to that entry can't continue because the fill has already started and it's too late. So those are the limits on merging. Merging can lead to much higher throughput of handling load misses in the second level cache and off chip, and a much faster restart upon fill. Okay, now let's look at the off-chip cache, the level 3 cache. This diagram shows the 21164 and with a third level cache implemented in static RAMs on a module. Both the tag store and the data store are implemented in static RAMs. The level 3 cache is direct map, but it's maintained as a superset of the on-chip associative level 2 cache through special logic on the chip. Now, up to 2 reads can be outstanding either in the level 3 cache or in memory, and those are kept in the bus address file as described before. Also, we have programmable wave pipelining in units of the CPU cycle time for this cache. Now, what I mean by wave pipelining is that data is allowed to change on the index bus, that is, the index to the RAMs is allowed to change prior to the chip reading the data buses. This is done in overlaps of the CPU cycle time. What this does is it leverages the minimum delay in the path through the caches to improve bandwidth. Note also that the level 3 cache is optional. Okay, the next slide shows the latency and bandwidths of the 3 cache levels. For loads that hit in the level 1 cache, the latency is 2 cycles. For loads that miss in the level 1 cache and hit in the level 2 cache, the latency is 8 cycles. And for loads that miss on the on-chip caches and hit in the off-chip cache, the latency is as little as 12 cycles, depending on the speed of the static RAMs. The bandwidths of the 3 cache levels are determined by the bytes per cycle. In the on-chip caches, there's 16 bytes per cycle, and that's sustainable continuously. At our typical cycle time, that translates to 4.8 gigabytes per second of bandwidth. Now, the off-chip cache can transfer 16 bytes every 4 cycles or longer, and that comes out to 4 bytes or less per cycle, so a peak bandwidth of 1.2 gigabytes per second at our typical operating frequency. The on-chip caches, the level 1 cache block size is 32 bytes, and the level 2 and level 3 cache block sizes are either 32 bytes or 64 bytes, depending on how you program the chip. Okay, at this point, I've given you an overview of the chip, and now I'm going to compare it to the preceding Alpha chips, and then I'm going to talk about performance. This slide compares the 21164, which is the new chip that I'm talking about, to the preceding Alphas, the 21064 and the 21064A, the A version of that chip being implemented in the same newer CMOS technology as our chip, the 21164. Now, the key points on the slide are reduced key latencies, a wider superscalar design, and a cycle time improvement that's greater than the technology offers. I should also have had a point on this slide that says non-blocking high-throughput memory subsystem. That's definitely an improvement over the previous generation. Looking at the latencies, the shift in byte operations have been reduced from 2 cycles of latency to 1 cycle. I've already discussed integer multiply. That's been reduced from 19 to 23 down to 8 to 16 cycles. The compare to branch bypass has reduced that path from 1 cycle to 0 cycles. The floating point latency is reduced by a third from 6 cycles to 4 cycles, and the level 1 data cache latency has been reduced by a third from 3 cycles to 2 cycles. Now, much of this improvement was gotten by working harder on the circuits, and some of it was got by the architecture. For example, the integer multiplier is improved by doing a wider multiplier array. Of course, the new chip, the 21164, is quad issue versus dual issue in the preceding chip. And the cycle time improvement comes from the CMOS technology, and the new chip is implemented in 0.5 micron CMOS technology, 0.5 micron drawn gates. When we simulate it at worst case environment, with typical SPICE models, typical devices that is, the chip runs at 300 megahertz. Now this is at least 10% more aggressive than the 21064A in the same technology. And I like to point out that at our typical operating frequency of 300 megahertz, our peak issue rate is 1.2 billion instructions per second. Okay, on to performance. Now the estimated performance results based on early measurements in prototype systems is better than 1 spec int 92 per megahertz, better than 1.5 spec floating point 92 per megahertz, and better than 2 tips per megahertz. All right. I got this slide for marketing. It shows the whole alpha family. The bottom line is the embedded family of alphas. The next line up is the high integration family. And the top line is the high performance family, of which the chip I'm talking about is a member. Shown on the left are the 3 existing products, the 21064 products, including the A version, which runs at 275 megahertz and is in the same technology as our chip. Our chip is shown as the EV5 family. And also you can see that there's alpha products planned for the future shown on this graph. So to summarize, the 21164 is a totally new alpha microprocessor. It has quad instruction issue. It has a large on-chip second-level cache that's write back. It has a high-throughput non-blocking memory subsystem. It achieves short latencies in all the functional units with a very fast CPU clock rate. And it runs extremely fast, typically 300 megahertz. It contains significant improvements over the previous generation, and it's the world's fastest microprocessor, highest performance microprocessor. And again, I'll point out that Pass 1 has been working for several months now. Okay, thank you.